All right, so we have been talking about work being forces as an object moves, and work either results in energy being put into a system or taken out of a system. What we want to do is relate this work to the overall motion of the system. So to get here, we know the net force acting on an object determines the acceleration of the object. The net force can be written as m, instead of acceleration, if you remember, we said acceleration is the derivative of the velocity with respect to time, the rate at which the velocity is changing. Now, we're going to do a little what I call trickery here. It's not really trickery. Work, if you've noticed, time hasn't been anywhere in our equation, right? Work, our fundamental equation, is the integral of force with respect to some sort of position, some sort of distance. So what I'm going to do is I'm going to take dv dt, so the derivative of the velocity with respect to time, and I'm going to multiply it by ds over ds. Now, why? Because I know where this is going, but ds over ds is simply the number 1. What I'm going to do is I'm going to swap these bottom pieces, so dv over ds times ds over dt. Well, we've seen this. ds dt, so the derivative of the position with respect to time is velocity. So what we're ending up here with is v, the velocity, times dv with respect to ds. So all I'm doing, it looks like total trickery, but it's really just a way to rewrite the variables. So now, instead of dv dt here, we're going to replace that with v times dv ds. That is an equivalent statement. I'm going to bring the ds portion up to the other side. And integrate both sides. Now, integral of a net force with respect to a displacement represents an overall total work done. So the net amount of work done on a system. On the right side, we're integrating with v, speed in this case, as our variable. Our lower limit is some initial speed. The upper limit is some final speed. Well, we have v in here already, so when I integrate this, I'm going to have v squared over 2, and then I need to evaluate that. So if I put in the upper limit first, I'm just bringing the 1/2 in front, so mv final squared over 2, or 1/2 mv final squared, minus 1/2 mv initial squared. I don't know if you happen to remember, but in the very first video, we defined the energy an object has because of its motion as kinetic energy. The equation for kinetic energy is 1/2 mv squared. So this equation over here is ultimately saying that the net overall work done on a system is equal to the final kinetic energy minus the initial kinetic energy. Or we could just write it as delta K, where we mean kinetic energy. The net overall work done on a system determines how this kinetic energy changes. Okay? If you remember in a previous video, we were talking about, I think it was Albert Einstein lowering a book at a constant speed. If the speed's constant, we know the acceleration is 0, so the force that Albert is exerting has to equal mg. Well, when we talk about net work, we mean the work done by Albert plus the work done by the force of gravity. The work done by Albert was negative because the force and the displacement were opposite, right? The delta S is pointing downwards. Albert's force is pointing upwards. So when we're using the equation F delta S cosine theta, we have force of Albert. Delta S is however far down it goes. Cosine, the angle, since Albert's force points straight up and the displacement is straight down, the angle between the force and the displacement is 180. That's where the negative sign came from. We could say it's just the work done by Albert is negative, his force times the distance. I'm going to call that y, just this y distance. The work done by gravity is positive because the force of gravity is mg. Delta S is the distance it's moved through. The angle between the force of gravity down and the motion down is 0. So we get mg, and then just y is the overall vertical distance the book moves. But in the case of a constant speed, Albert's force and the force of gravity were the same. So the net overall work done was 0, which explains, if we go back up, this net work is equal to the change in kinetic energy, or we can just write it as this change, the 1/2 mv final squared minus 1/2 mv initial squared. Well, if this has to be 0, then these speeds have to be the same. V final has to equal the initial. So the speed must be constant. So this equation is called the work kinetic energy theorem. The work is always related to the forces. The kinetic energy is related to the speed. So we are able to relate forces to speeds directly, relating work to kinetic energy. As you start working on problems in this section, you will probably notice that many of the problems you could technically solve using Newton's second law and kinematic equations. When it comes to our test, though, you will be asked to solve the problems using concepts from this section. So, as of now, for any motion problem where you're trying to relate a speed and a distance and a force, you're going to use this work kinetic energy theorem. So, net work equals change in K is the same thing as what's in this box. We've just substituted in the final kinetic energy in terms of 1/2 mv final squared, and then the 1/2 mv initial squared is the initial kinetic energy. So any problem relating the forces to speeds, this is where we will want to jump to. For those that have had physics before and you have used conservation of energy, we will get there quickly in chapter 10. I'm going to kind of speed through this part because I like using conservation of energy better. For those that conservation of energy, that term is new to, don't worry about it, that's okay. We'll explain it as we get into chapter 10. It's just another way of writing this work kinetic energy theorem by also accounting for potential energy and thermal energy. So we'll get there. For now, here we are. This is how we will relate forces and speeds.